Imagine trying to manually monitor, update, and restart tens of thousands of individual software containers across a massive enterprise application. As traffic spikes and servers fail, you face a logistical nightmare of cascading errors and downtime. To stop that chaos, engineers use Kubernetes. It is an open-source system built specifically to automate the deployment, scaling, and management of those thousands of containers, so human engineers do not have to. Looking at this topology map, you see how Kubernetes handles that scale by splitting its universe into two distinct halves. On one side is the control plane, making global decisions. On the other side are worker nodes executing workloads. Rather than thinking about this as a rack of hardware, it makes more sense to look at it like a highly structured Michelin star restaurant brigade. A busy restaurant survives a Saturday night rush by strictly separating the front-of-house management taking orders from the chefs cooking the food in the back. Kubernetes applies that exact logic to software, separating state management from code execution to achieve scale without collapse. The process starts when a developer issues a command, like kubectl apply, to deploy a new application. In our restaurant, this is a customer walking through the front doors to place an order. This diagram shows the very first point of contact in the control plane, the API server. Think of it as the head waiter. It is the absolute gatekeeper and the only component allowed to communicate with the outside world. It scans your request, checks your credentials, and either turns you away or accepts the order. Once accepted, the API server writes it down in etcd. Etcd is the restaurant's central order notepad, a highly available, deeply secured database that acts as the authoritative record for the cluster. It stores the exact desired state the developer just asked for. This system operates on a very strict rule. If a request or a piece of data is not physically recorded in that etcd database, it does not exist in the cluster. Now we bring in the controller manager, which acts like a restaurant manager on the floor. As you can see in the diagram, it continuously scans etcd, looking for any discrepancy between the blueprint you requested and the reality currently running on the network. When the manager spots a new order, it hands it to the scheduler, our host. The scheduler evaluates the specific CPU and memory requirements of your application, checks the capacity of all the available worker nodes, and finds the perfect open spot to host your app. Notice what just happened. The control plane authenticated your identity, logged your request, and planned the deployment strategy, all without actually running a single line of your application code. With the planning done, the focus shifts away from the management layer. We are moving into the back of house, the worker nodes, where the actual compute muscle lives. Each worker node has a local agent installed called a kubelet. The kubelet is the chef assigned to the station. It receives that validated ticket from the control plane and gets to work. It reaches out to your registry, pulls down the necessary software container images, and starts firing up the pods to run your application. At this point, the developer's initial request is fully realized. The code is actively running, it is healthy, and it is ready to serve live user traffic. By creating this specialized handoff from the user placing the order to the individual node executing it, the system establishes precision and absolute system security and accountability for every workload launched. Deploying an application is just the initial task. The system's core strength is its continuous observation loop. Imagine a scenario where a piece of hardware catches fire or a server physically fails mid-operation. It is the equivalent of a chef dropping a fully plated meal during a busy dinner rush. As soon as the node goes down, a red error pulse alerts the controller manager. It sees the cluster no longer matches the blueprint in etcd. The scheduler immediately finds a brand new, healthy node. It reroutes the workload pathway, bypassing the damaged hardware. A new kubelet on that healthy server receives the replacement order and spins up fresh containers instantly, restoring the application before the end user even notices a disruption. Through all of this, no pagers went off. No engineers had to wake up at 3 in the morning to manually restart a crashed server. The system identified the damage and healed itself autonomously. By dividing its architecture into specialized roles that constantly communicate via a central API, Kubernetes transformed infrastructure from a manual chore into a self-healing system that can manage global workloads without human oversight.